A very warm welcome to everyone. My name is Vishal Pancheta and I will be presenting a small seminar on cognitive computing with artificial neural networks and how do we write and visualize different kind of neural networks using TensorFlow and Tensorboard. So cognitive computing, let's start off with the introduction. Cognitive computing is mimicking of human behavior and thought process by a computing unit. It is the branch of computer science that deals with imparting human-like processing and thought process in a computing unit. Thus, a major contributor to the revolution of AI in modern era. Now, artificial intelligence in modern era has touched millions of lives, as you all can guess. AI has been the core of research in modern day and is expected to move forward with an exponential rise. AI today makes most of your decisions. It decides what ads you watch online, what product you might buy, what product you might be interested in. It filters out your spam. It prevents you from different kind of phishing attacks. So let's see what some major examples of cognitive computing might be. The first thing that comes to mind is natural language processing, which is a field of artificial intelligence that deals with understanding and working of natural language and how everyday day-to-day life, how we converse and how it can be implemented in computer science, and the knowledge of language without proper syntactical grammar that is predefined in languages of a computer. Some other fields are machine learning and deep learning, where it helps a computer to understand patterns and images and other real life entities and solve uncodable problems, or the products which require some sort of thinking by a human brain. Thus, AI is defined as the ability of a computer to solve problems that would require otherwise some sort of processing if done by a human or by any other sentient entity. So in today's seminar, we'll be focusing on image recognition. We'll be trying to write a neural network which tries to classify handwritten digits, which is a very simple problem to solve, but our aim is not to solve the problem, but instead look at how neural network behaves by visualizing every entity of the network. So most of the development in today's world is done using modern machine learning techniques and deep neural networks. So as you can see, neural networks is a subset of deep learning, which is in turn a subset of machine learning. And AI is just a field that encompasses all of these fields. So even though we are the ones who design these neural networks, there are certain problems with interpretability of a neural network. So neural network can in some sort be a black box. Even if we see the output, all the parameters and all the biases with all the tensors are good enough for a computer, but it's very hard to understand if you're a human. So it's very hard to debug, or in case of any debug output, it's very hard to visualize what's happening. So for interpretability of models, there have been a lot of recent approaches which let a common computer scientist who hasn't designed a neural network, or someone who is looking at the neural net from a layman perspective. There have been a lot of tool builds for this. One of them is Tensorboard, which lets you visualize the code written in TensorFlow. As our model is a black box, Tensorboard can be thought of a flashlight. It gives all the graphic visualizations of data and embedding with graphs for really good understanding of data and model, along with parameters and other hyperparameters. So Tensorboard is a GUI tool that runs on a web app over the top of TensorFlow app that is developed by Google. It comes packaged with TensorFlow and is very, very useful when it comes to building neural networks, which we will be exploring today. So starting off with the installation of the tool, I will be working on Anaconda, which is a scientific computing bundle which has a lot of computing libraries for tensors and arrays. So tensors are nothing but n-dimensional arrays. So to download Anaconda, you can go to the URL anaconda.org, where click on download Anaconda, and depending on your operating system, you can download your installer. I'll be working on Windows 64 graphical, so as I have 64-bit Windows, I'll be downloading the 64-bit installer for Windows, preferably for Python 2.6. You can go for Python 2.7 as well, depending on your choice of Python and what you prefer. So I'll be pausing the video here till it gets downloaded, and I'll be resuming after the download completes. Okay, so now that we have Anaconda downloaded, we'll proceed with the installation. Installation is basic executable files, so just follow whatever the instructions. You can use all users or just me. I'll prefer all users. It gives the task for admin privileges and wherever you want to save. So browse to whatever destination you want it in. I prefer my own locations, and if you want, you can add Anaconda to system path. I prefer not to. You can do it manually, but what this does is it automatically adds it to path, and I'll install. So it'll take some time to install because it's a heavy software. I'll pause the video. Okay, now that the installation has finished, Anaconda installs two different applications here. One is Anaconda Prompt and one is Anaconda Navigator. You can go ahead with either. I prefer the prompt, so I'll open prompt. This is basically like your own command line tool. So every command prompt application or every command line task or any command line command would work here basically. So first what we want to do is we want to initialize an environment. So what we do is we do conda create -n and then our environment name, that is seminar, and we want to specify which Python we're going to use. So we use Python 3.6 here, and we press enter, which creates a new environment. So conda is used for creating environments. It will first solve for environment and see which all dependencies are not installed for this, and it might tell you which dependencies to install and which dependencies which are required for this to happen right now. So anything that is not installed will be asked to install, and as you can see, press Y and it will download all the dependencies that are missing. So it's down, as you can see, it's downloading wheel, which is a Python package, then pip, which is used to install Python packages, setup tools, again the same thing, Python 3.6, as we mentioned that it should be Python 3.6 environment here, and it will download other runtime libraries and every certificate that is required for installation and running of this environment. So it might take some time depending on how many libraries your computer is missing. It might be the case where everything is already installed, and it will just create a transaction, verify the transaction, and finish off with the creating of an environment. Might take some time in verifying transaction because it goes through the database. Now the environment is created, but we are still in base. This curly braces, sorry, this parenthesis that you see here, the environment inside this is the environment you're using. So we're currently using base, which we don't want. We want our environment named seminar. So what we're going to do is we're gonna do conda activate seminar, which will activate our environment of seminar. So we're inside our seminar environment now. Now if we type Python here, it will take us to a Python shell, but this is bare bone shell right now because we haven't installed any libraries. This is just the starting. So what we do is press Ctrl Z and enter to get out of the shell, and we install TensorFlow. So we just do conda install TensorFlow, and it will see which all libraries are used for TensorFlow and which all dependencies are required. So TensorFlow requires these many libraries, and none of these are installed because this is a new environment and there's nothing, just a bare bone Python is available. So we go ahead and we install all these libraries. It will take some time to download these libraries, and depending on the size of the libraries and your internet speed, it might take anywhere between 2 to 5 minutes, or even more than that if the internet speed is slow. Now open a fresh Anaconda prompt. Make sure you're running it as administrator, and since again we're in base, we'll have to shift back, conda activate seminar, and it will activate seminar over here. Let's see if our Tensorboard is installed properly. What we do is write Tensorboard log dir and current working directory. So we are providing a log directory, which I'll be explaining in a while, and we're providing the current working directory as our log directory right now. Now what happens here is, if you can see, sometimes this will not work because the Anaconda prompt will not have access to the internet files. So you have access is denied error here. So in these kind of matters, what you do is you close this again and just run the above command with another flag as host 127.0.0.1, which will run the application on localhost. Now again, here you might find some access denied error, but it will still work. I mean, Tensorboard right now is a little buggy, but see, you get access is denied error, but if you open localhost, you'll realize that it's working. So you just copy this URL, you open a window or a web browser, and you go to that particular URL, and you can see that Tensorboard is working. So it'll open the GUI, but there will be nothing here because we haven't done any coding yet. So scalars, images, all of these tabs I'll be explaining once we get into the code and once we come back to Tensorboard. Right now we're just checking if it's working. So our GUI is installed, our entire tool is installed. Let's start with the code. So let's dive into the code for now. The code is written in TensorFlow, which is a tensor programming library in Python. I won't be writing the code again, but I will be explaining the code, and this code will be available in the description, which you can download and run. The first thing is loading the dataset, which is essentially probably the most important part, because the dataset is not locally available, and we will probably have to download the dataset. But TensorFlow has this datasets library which automatically downloads datasets if they are missing. So it's just a partial code where you just have to write what sort of dataset you need, and it downloads on its own. So the first thing is a log directory. This is where the dataset would be downloaded, and all the logs would be registered for debugging in Tensorboard. Labels and sprites are files. Sprites is just an image which has all the test images. It has random images where you have handwritten digits, and it has total of 1024 handwritten characters, not characters but digits. And labels are the labels of all those 1024 images. It's essentially just a one image, and all those 1024 digits are collated into one image. Next is mnist, which is a variable that is of type dataset, and what it does is it has a training directory of log directory, which is where the dataset would be downloaded, and one hot true. So one hot here refers to one hot vectors. One hot vectors are nothing but vectors where only one element of the vector is high and everything else is low. So let's say if we want to represent all the 10 digits from 0 to 9, we'll have 10 elements in the vector, and if it represents 0, we'll have 1 at the 0th index. If it has to represent 1, it will have 1 at the first index, and everything else will be 0. So in case of 2, it will have 1 at index 2 and everything else will be 0, and so on. Where in case of 9, it will be 8 zeros and then a 1. The next thing that comes is basic structure of a neuron. How do we define neuron, and how will we define our neural network, because neuron is the basic entity of a neural network, and what will happen in neuron and what sort of operations would happen as a group of neurons where you define a layer. So layer is basically all the neurons collated together which receive input from a lower layer and give output to an upper layer. So a structure of neuron will have these three parts. The first thing would be parameters, weights and biases. Then a neuron function, that is this neuron, what function it performs. In case here it's summing function, that is just a simple linear sum. And an activation function, which is performed on the output of this. So this thing as a total is called a neuron. So in case of parameters, weights and biases, these are the things which are specific to a neuron, and these are the things that will be optimized during a training. So weights are these inputs. So every weight corresponds to one element of an input. So if it's a vector of m dimensions, it will have m weights and one bias. So bias is specific only to a neuron. It is not dependent on any input, and one neuron has only one bias. This summing function that is happening here, which can be any other function in mathematics. This is just a simple example of neuron. So any mathematical function that happens here on basis of weights, inputs and biases will result in a output of nu, which is just a neuron function output, and there is an activation function that takes that output and gives another output, which generally is a non-linear output. So basically the function here is non-linear, and it induces non-linearity so that the data is separable if it is not linearly separable in any condition. So next is defining the layers of any neural network. So we'll be working with convolution layers and fully connected layers. So convolution layer is essentially just a convolutional neural network layer where you have input of the basic input of any layer. It can be any vector or any image. In this case, it's just a vector. You have the size in and the size out, which is the size of input and the size of output that is given by the layer, and the name here is just given as conv. You can define name as anything. I prefer conv. So here we have w and b, which are tf dot variable. So this is TensorFlow variable. Now w is the weights and b is the bias. So b is just a one variable which is just constant, and name as B, which just stands for bias. Now this constant starts off with 0.1, but it might change. Like here you have truncated normal 5 5 size in size out, so it's just 4-dimensional array. So variable of weight type will be a 4-dimensional array which has input size, output size, and 5 5. 5 5 is the size of kernel. So kernel is something that can be thought of as a window which has stencil on top of it. So that kernel would be going across the entire image. So it's just a small window that goes across the entire image, matching if that particular stencil is present in any part of the image, just to detect it. Next is conv, which is a convolutional operation which is predefined in tf.nn. nn here is neural network. So it does a convolution operation on input with weights and stride. Stride is how much that kernel would shift in every iteration. So let's say the window shifts by 1 unit or 2 unit or 3 unit or 4 units. So in this case it's a 5x5 window, or the size of the kernel is 5x5. So it'll just shift by 1 unit. So 4 units would be repeated again and 1 new unit would come across the input. Now ReLU is the activation function. ReLU here means rectified linear unit. So rectified linear unit is if in case of any negative output, it will rectify it to positive or 0. So any positive output is given directly as positive output. In case of any negative output, it gives out 0. So what we do here is we add conv plus bias. So as I mentioned, bias was a singular term, and conv is happening on the input and the weights. So input and weight are convoluted and bias is added, and then later on the rectified linear unit, which is the activation, happens. So as you can see in the previous slide, we have all the weights which are in convolution with the input here, and finally over here at the summing junction, everything is summed together. So all the weights which are convoluted with the input is added to the bias, and then the output of this is given to the activation function, which in case here is a ReLU operation. So ReLU does activation of convolution plus the bias, and which is the final activation. Now here tf.summary.histogram weights w, what it does is it gives a summary of all the weights. So basically if weights change, so since this is a layer, so there'll be millions and millions of weights depending on the size in and size out, and they will keep on varying according to the training process. So what it does is it starts writing a summary in histogram model. So histogram is just type of summary. There can be histogram summary, pie graph summary, and other sort of summaries. You can have image summaries as well. So it starts writing summaries of weights, biases, and all the activation functions. So this is just for logging of debugs, and just so that in case we have an error, we can open Tensorboard and look at these histogram models. Now finally what we do is we return the max pool of it. Now what max pool does is instead of returning the higher dimensional data that we have here, because there are huge number of dimensions in an image, what we do is we take the most prominent feature of that particular region. So if there's a kernel size of 1221, so it's a 4-dimensional kernel, in that region whichever thing or whichever field or whichever vector is the most prominent, that will be pulled out. So in case of an image which has white background and 1 digit written on top of it, the most important thing in that is the digit. So all the background will be removed and only the digit will be pulled out of the image, which is what we want in these kind of cases. So this was convolution layers. We will have variable convolution layers in our code, which I will explain once we get into the code. This is just definition of convolution layers. We might have one convolution layer, we might have two convolution layers. So what we are trying to do here is we'll have a loop of different number of convolution layers and see which convolution layer or how many convolution layers give you the highest accuracy, because accuracy can never be measured on paper, and it always has to be a trial and error method. The next type of layer that comes up is a fully connected layer. Now, fully connected layer means that every neuron in a previous layer, the output of every neuron in a previous layer will be connected to the input of every neuron in the next layer. So it's fully connected, as in the most number of connections you can have. So if in case the input has 3 neurons and the fully connected layer has 4 neurons, there will be a total of 3 into 4, that is 12 connections from first layer to the second layer, because every neuron of first layer will be connected to the input of the next layer. So every neuron in a fully connected layer has an input that is drawn from the output of every neuron in the previous layer. So we define fully connected layer as input, which is again a vector in this case, size in, which is the size of the input vector, size out, which is the size of the output that is going from this neuron. So output can be number of neurons basically here. And I define this as FC, which is fully connected. So again, we have two variables, weights and biases here. Weights again is a two-dimensional vector here because it's a size in and size out. We do not have other dimensions because it's connected to everything. Previous case we had 5 and 5. So 5 nearing neurons in the previous layer would contribute to the input of next neuron. Here we have all the neurons, so we don't define it. We can just simply connect all the input neurons to a particular fully connected neuron here. Now activation here is tf.matmul. Matmul is matrix multiplication. Input is again a tensor and weight, so we have multiplication of input to weights and biases are added. So this is the activation here. We do not have a separate activation function in case of fully connected layers, because matrix multiplication in itself is a non-linear function, so there's no need of having a non-linearity in this case. Previously we used to have just addition, which is a linear function, so we had a non-linearity in form of a rectified linear unit. Over here matrix multiplication itself is a non-linear function, so we don't need to have a non-linearity introduced here. Again, the summary of histogram models of weights, biases and activations, and I'm just returning the act that was calculated here. So this defines a fully connected layer. Now something for Tensorboard. This is probably the most important and the interesting part of Tensorboard. We call it the embeddings projector, where all the images and all the input data, no matter how big it is and how many dimensions it has, it's brought down into 3 dimensions and plotted in a 3D graph. So if you open the projector or the embeddings part in Tensorboard, you'll find every input image or every test image or any other sort of data that you have trained it on mapped down to 3 dimensions, and it will be plotted in 3 dimensions, and you can do multiple operations on it. So how we do that is we initialize embedding as a variable, which is starting off with zeros, because we'll be calculating it later. So I won't go into detail here, but what we do here is we initialize a file writer object, which writes the embeddings into a file so that Tensorboard can read it. We have configurations, which is addition of all the embeddings in the file writer object, and we have sprite, which as I mentioned earlier is the image of all the digits, and we have labels. So what it does is it colors those sprites as per the labels. So if all the ones would be colored in one particular color, all the twos would be colored in one color, all the threes would be colored in a different color. So now what we do is we specify the width and height of every thumbnail, because as I mentioned, Sprite is just one image. Now one image has 28 cross 28 digits, so it will have 28 rows and 28 columns of different digits. So it's one image which has 28 digits per row and total of 28 rows. So it bifurcates one image into 28 cross 28 images, and every image responds to or corresponds to one digit. Over here what we do is we just use the projector item which visualizes the embeddings, which is defined here, and it writes to the file writer object so that it flushes to the disk, and the configuration file which will be used by Tensorboard. Finally, we come to the part where we run the model and it gets trained. So we define our main function. So as I mentioned, we'll be comparing different learning rates and different number of layers, and we'll see which layer and which learning rate gives us the best accuracy. So we'll start off with two learning rates. One would be 10 power minus 3 and the other one would be 10 power minus 4. So in these two learning rates, we'll see whichever learning rate gives us the most accuracy. So use 2fc here is just a binary variable which is always true, so we'll always have two fully connected layers. Fc stands for two fully connected layers, and two conv layers will be false or true. So we can have one conv layer and two conv layers. So what we have is we have four models, two with learning rate 10 power minus 3. So it will have two fully connected layers, and one of the models will have one conv layer and the other model will have two conv layers. Then one more bifurcation where we have learning rate as 10 power minus 4, and one model will have two conv layers and one model will have one conv layer. Now here hparam is the hyperparameter tuning. So we start off our hyperparameter tuning and the parameter tuning. So basically we're starting off our learning here. So we start our training of the model as learning rate and all the two variables. So we can have learning rate with something, and we have defined which all variables will be used. So this is just a structure of your neural network here. We have learning rate, we have fully connected layers, and we have convolution layers. So we're just printing that starting run of number, which is basically the epoch of whichever hyperparameter here. And MNIST model is where the actual training is happening. MNIST model is defined as learning rate, 2fc, 2conv, hparam. So hyperparameters are the parameters which are supposed to be tuned for this MNIST model. We have the learning rate at which the learning would happen. We have the fully connected layers, and we have the convolution layers. So this is the code that I mentioned will be available in the description. It has everything that we defined right now. So it has conv layers, it has fully connected layers, it has the embeddings, and it has the training loop in main. So we will be running this. To run this, again we have here the Sprite PNG. As I mentioned, Sprite has all those images, 28 cross 28 images. It's just one image, but it has 28 rows and columns of different handwritten digits, as you can see here. And labels are again just a TSV file of all the labels that are in the Sprite. Okay, to run this, just type python mnist.py, and it will start executing the code. First of all, it will create a folder named tmp here in this, which is a temporary folder, and which is our log directory, as I mentioned, and it will create all inside this tmp. It'll download the data, which is these images, and it'll start with the execution of all the models. So starting off with LR 10 minus 3, so this is learning rate of 10 power minus 3, conv 1 and fully connected 2. If you get these instruction errors, doesn't matter, because these are just warning and telling you that if you compile TensorFlow from source, you can get better results and faster accuracies. So this might take some time, the training, because first of all, the data set is big, it's about 10 MB, and it's very model specific, and which kind of architecture you're using. So I'll show the output that comes after the execution of the entire training. Okay, so after you run the model, the output will be somehow in this form. It says successfully downloaded train images, train labels. So this is, till here is where the download of data set is happening. It might take some time. Data set is about 10 MB as I mentioned. And then you'll have runs starting for every model. So we have 4 models. The first one is learning rate 10 power minus 3, 1 conv layer, 2 fully connected layers. So we'll print every 500 epochs. So we'll have 2000 epochs for every model, and we'll keep on printing for every 500 epochs. Now this might take some time because it's a very heavy model, and training a neural network takes a lot of time. So might take a few hours as well, depending on what sort of architecture you're using. I'm using TensorFlow GPU, so it does faster calculation on a GPU. If you're using TensorFlow CPU, it might be a little slow because GPU is much suited for matrix multiplication and matrix operations. So depending on your architecture, it will take some time. So once finally the entire execution happens, it automatically gives a message saying that the training is completed, and you can proceed forward with logging into Tensorboard to visualize your neural network. So to start your flashlight or Tensorboard in this case, what you do is run tensorboard space -- log dir, which is a flag, and space the path to your log directory. We define this as temp mnest example. Inside that we'll have all the logs and debugs stored. Now Tensorboard would run on port number 6006 by default. So 6006 has a typical funda where inverted is goog, and goog.le is a domain by Google, which is probably just an inside joke by the Tensorboard people. So let's see if Tensorboard runs. Okay, so now you can see the execution has stopped, the model has trained, and it is giving you directions as to how to run the Tensorboard. So to run Tensorboard, just type tensorboard log dir and provide the log directory as tmp/mnest tutorial. So this is the folder tmp where all the log directories are stored. So this is where the data was downloaded, and this is where all the logs are stored. So these are all the 4 models that we have trained, and these are the logs that are stored for this particular model. So what you do is you just type tensorboard log dir temp/mnest tutorial, which is the log directory, and provide host as 127.0.0.1 just to run it locally. Now once you do it, go to the browser and type the same URL, and you'll come to Tensorboard where Tensorboard web app would be running. And now we can see or visualize everything that we have done till far. So the first thing I always do is go to the graph tab. This is where all the graphs of your neural network would be initialized. So you can see all the layers that are there in your neural network. You can even expand these layers. So let's say this is the conv layer, and we try to expand this layer by double clicking, and it will show what all operations are being done. So W is the variable that we assign to weights, and weights are being in convolution with the input that was supposed to be there. The x vector is the input, and as you can see, it's in convolution with the weights, which is then added to the bias, as bias was a single term, and then ReLU activation is performed, and the max pool is performed like we defined back then. So this is for one model. There are two fully connected layers. So if you remember, there were two fully connected layers in all the 4 models. This is for one model where we have learning rate as 10 power minus 4 and 1 convolution. If we check, we have other 4 models as well. We can click on any model to see the graph. Here we have 2 convolution layers, conv1 and conv2. Now there are multiple features here that you can see. You can realize that layers with the same architecture are colored in the same color. Now this might seem like a very trivial thing, but initially when TensorFlow was being developed, there was an error with the inception model, and everybody thought, okay fine, TensorFlow doesn't work. But turns out there was one slight mismatch of one wrong wiring in one layer, because of which the entire model was not being trained. And they developed this so that TensorFlow automatically realizes if the given layer it belongs to one particular model or not. So 2 fully connected layers are colored the same, 2 convolution layers are colored the same. Now if you go up, this is the accuracy method. This is where your accuracy is defined. You can see what all parameters it takes, and this is not what we defined, this is what accuracy was defined as earlier. And xent here is the cross entropy loss. This is our error function, and all of this, if you zoom in, all of this is connected to train. Train here is the process where everything would be, where the training would happen. And you can see all the layers are connected to this, because every layer has some parameter that is supposed to be tuned during training. So there are other things here. You can see trace inputs, where in trace input you click on one layer and it tells you which all layers contribute to the input of that particular layer. So let's say you try trace input for conv2, so only conv1 is the layer that contributes to the input of this. Now this is a very small graph, so this is very intuitive, but then in case of large graphs with like thousands of layers, this is very important, because you have to realize and you have to understand which layers contribute to the input of other layers. So next thing is color by device. Now everything is stored on the GPU or on the CPU, so everything is colored correctly in the same order and colored as same, because everything is stored on one particular memory. But then if you have mix of different GPUs and CPUs, you can see which all parameters are saved on which particular device, which will be colored in that particular order. So the next thing I prefer going to is the scalars. This is where your actual graphs would come up. Now this is the accuracy graph. You can maximize it, and you can smoothen the graph here. Let's smoothen it to a readable level. So this is for all the 4 models. You can see the accuracy of all the models. You can see singularly as well. So this is for learning rate 10 power minus 3 and 2 convolution and 2 fully connected layers. The final accuracy is about 98% plus, so it's around 99% actually. And if you select all 4 of them, you can compare accuracies of different models. So you can see this model, which is learning rate of 10 power minus 4 and only 1 convolution layer, has accuracy which is about 96%, which is very laughable when it comes to MNIST, because MNIST is a very good data set and anything less than 99% is not good enough. Other 3 layers or other 3 architectures actually perform well, with the learning rate of 10 power minus 3 performing better than learning rate of 10 power minus 4. Now this is experimentally proven that learning rate of 10 power minus 3 is actually a very good learning rate if you don't want anything, if you don't know which learning rate to start from. So learning rate 10 power minus 3, both the models are around 98 to 99% accurate, which is very good provided that we haven't trained it for a long time. Okay, so the next thing is the loss function. You can see the loss function again has 4 graphs. You can smoothen it again, and you can see that learning rate 10 power minus 4 with the 2 conv layers has higher error. So this architecture is probably not suited because the accuracy is low and the error is high. And this is cross entropy loss, which is a good measure of your error here. You can substitute cross entropy loss with error, but other 3 models are performing well as mentioned, and again the models with learning rate 10 power minus 3 have the least loss. In the images tab, you can see all the input images that have gone to the models. You can see the actual size of the images is this big. So this is 8, this is 5, and you can see which all time steps, which all images were there. So at 1425th iteration, the input was 6, and at 1125th iteration, the input was 1. This is to the model of 10 power minus 4 learning rate, conv 1 types. So this is given for all the 4 types of models here. This is again, you have filters here to see and just visualize one sort of model. So you have all the models and all the inputs initialized here. Okay, so next comes distributions. Distributions is where all the activations and all the biases can be seen. So let's see how the activations are. So activation function for conv1 was the ReLU function, if you remember. So ReLU is rectified. So anything below 0 is chopped off. So everything is above 0. So it varies between 0 to 0.3, which is good because it should be less than 1, as you don't want exploding gradients. Again, the activations in the other model, every model has it above 0. Now the biases can vary from model to model because biases are very independent, and you do not have any sort of intuition as to how the biases would go. So you can realize that, you can see that the biases are very different in both the models. So this is 10 power minus 4 learning rate, this is 10 power minus 3 learning rate with the same architecture, and the biases vary by quite a lot. So at the starting in learning rate, which was less, you can see the biases are not changed much because the learning rate is low. But in case of a little higher learning rate, the biases initially have split up. So this is learning a little slow, which is provided given that the learning rate was less, and this is learning really fast. That leads to good training accuracy, but we don't want higher learning rates because then the model might overfit, or you might shoot the local minima, and there are multiple issues with higher learning rate as well. Next is the weights. Weights are generally bound in one particular region because most of the weights are dependent on the input, and input usually does not change. So as you can see, the weights here are bound between minus 0.15 to plus 0.15, which is very linear, and weights usually do not change that much. And in case of the other model also, they're bound by the higher and the lower order. You can see that was for conv1 layer. Now you have conv2 layer. You can see that it's the same thing here as well. It talks about the activations and weights and biases again. Moving on to histogram. Now this is 2D projections. Histograms project it in 3D. So this is one of my favorite part about Tensorboard. You can visualize all the neurons at the same time. So given any neuron, so these are the neuron numbers and these are the activations. So in previous case, you had distribution given as mean, median and mode, as in just a representative of a group. Here you have all the individual models given and all the individual activations and means given. So this is the activation which lies between point, this is about 0.12 for almost every neuron here. And I like the visualization as well. This is the 3D visualization. There are other visualizations like overlay. In case of overlay, it's not 3D, but it is an overlay on top of each other. So if it is offset, it gives a 3D model, which I prefer. And as you can see, you can hover over any given entity to understand what the value is and which neuron it corresponds to. Again, the same thing. This is for conv1, and next is conv2 layer. Again, you have activation functions and weights and biases. So you can see the biases are again bound for 10 power minus 4. Biases are probably mostly constant because it's not learning much. The learning rate is a little slow. And for 10 power minus 3, it varies quite a lot. It starts off with 3 and then goes on to 7. And the weights are distributed. So you can see here that the weights and the biases are very different in the two layers, even though the layer architecture is same. Now this happens because of different representations and different features. Some features are very important, which are extracted in the upper layers as in the first layers, and some features are not so important, which are extracted in the further layers. Now depending on the feature, the weights and biases will change. So most important features will be extracted in the first layer. That's why weights and biases are designed in that way, and the neural network does it automatically. It automatically learns the mathematical function that represents all these weights and biases. Coming off to projector. Now this is probably the most important and the most interesting part of Tensorboard. As I mentioned, this is where the embeddings would be projected. So everything in the knowledge space is boiled down to 3 dimensions. Now this can be done with 2 different techniques. Now as you can see, all the images and all the data is plotted in 3 dimension here. You can change the color so you can visualize it better. So all the classes are colored differently here. Now you can see all the ones are clubbed together. So 1 is a very distinct digit, so it doesn't take much time to club 1 together. Now any new incoming digit, if it lies somewhere in here, so it's most probably going to be a 1. So 1 is bifurcated very easily. Other digits like 7 and 9 go together because they look almost the same. So 7 and 9 lie almost in the same area. So now that there are, as I mentioned, shifting it down to 3 dimension has 2 different techniques. One is PCA, this is principal component analysis. What it does is takes the 3 major dimensions and plots it in order of those 3 dimensions. So component 1, component 2, component 3. Component 1 is the feature with the highest variance, second with the second highest variance, and third with the third highest variance, which is more than enough to bifurcate the digits. But then there's something else called tsna. This is T distributed stochastic neighbor embedding. This is my favorite. Now if you click on tsna, it will start computing tsna, and it will try to club all the classes into one, and you'll probably will have to wait for some iterations to see good results here. Now let's say it's 300. Let's just stop it here once and see what's happening here. So you can see 1 is again bifurcated. Now we haven't given much time, so there might be some errors. So you can see 0 is also a very distinct digit, so 0 is also taken out. And let's see some kind of misclassifications here. Let's try to find some misclassifications in these. Now okay, so this 8 here is classified in the group of 9. So if you can see, this 8 is probably, it looks like a 9, so that's not a model error here. It's probably the most 9 looking 8 you can find because the lower loop is not there. So model is doing a good job here. Again, this 4 looks more like a 9. Again, this 4 looks like a 4, so there's some sort of model error here. And Yeah, so 6 and zeros, there might be some zeros in 6, and again, so this is where you visualize all the graphs and how your model is working. And given this, I believe our model is working pretty good because we don't have that much of training here done. And there are multiple options here. You can see this is for this model. Let's try for 10 power minus 3 with 2 con, which should give us better results. And let's start the t-snare for the same number of iterations. So starting t-snare for, we did around 260 iterations for the last model. We're gonna do the same number of iterations in this model as well. Okay, so let's stop here. As you can see, again, ones are taken out pretty easily. This 4 is classified as 1, which is, I guess, okay, because this sort mode looks more like a 1 than a 4. Now look at some sort of errors. This 8 is classified as 3, which is, I guess, some sort of accuracy error. And 2s are clubbed together pretty good, which you can see here. 7s are clubbed together nicely. 9s are different from 7s, which is good to see. Again, there's one 8 classified as 9, which again looks more like a 9 than an 8. And this 8 is classified as 4, and it looks like a 4 than an 8. So I guess this model is working great. And click on reset to make it project everything in 3D. There are other options, like you have bounding box. You can select which all elements do you want. So this bounding box has selected these many elements. Most of them are 2s and 0s. There's an edit current section, so you can edit the labels of any given image. If you find that there are some sort of errors in the training data or in the test data, you can change it here. There is enable disable night mode, which I believe is just a gimmick. And then there is enable 3D mode, which just makes it a little more easy to visualize, because it changes the image's size and makes them small. It's actually the actual image size. You can't see the images, you can just see the labels here. It's just a data point. If you remove this, you can actually see the images as well. So that was Tensorboard, which helps us visualize our neural networks and we can debug our neural networks with the given information. In case of any errors, we can look up in the graphs and plots of errors and accuracies to understand where the error is happening.